or just like overall.
I got 100% on the writing portion.
Alright. Well, that's because I just set up on the thing on the computer.
Good Monday morning, ladies and gentlemen. How are we doing today? Other than the one that's up here sitting there waiting to take?
I think it is.
Josie!
You don't have the periodic table memorized, guys. The periodic table of elements memorized. Right?
Unplug it. There you go. Do I have it memorized? Heck no, why?
Did Mr. Arts have it memorized?
No.
Okay.
Now, do I know the atomic number and masses of some of the more commonly used elements? Sure, go ahead. But do I have the whole thing memorized? No.
Okay. That's all.
So, that's it?
That's it.
Okay, good. I need 3 volunteers, ladies and gentlemen. I need 3 volunteers. Do you want to know what you're volunteering for first?
No.
No? Okay. Who's our third? I got 2 over there. I got 2 over here. Who's my third?
Wait.
Well, I would have thought that would have been something you wanted to know, but Phoebe, come up and draw me a picture of what an atom looks like.
Oh.
Not to scale.
What does that mean?
Not to its actual size.
Do you want a Bohr model?
Oh, I want to know what you think the atom looks like. Anybody else?
Isn't it like boom? There's a circle, right? There's something there.
Here's the
something
thing.
there.
It's your idea of what the atom looks like. Don't confer with Phoebe on your idea.
Something like that. I don't know. I'm trying to think of vocabulary.
Anyone else?
Yeah. Oh no. Something like that. Wait, I gotta use like context clues. Yeah, there's like. Oh wait.
You can have this section of the board over here since they seem to be going over there. Phoebe just wants to draw, I think, on the board.
That's it.
I was trying to put these here, or do you want?
Just set them on there, please. Thank you.
That's all.
Phoebe, how can you have 3 different models of what the atom
There's
looks like?
different models of each, like as it went on.
Oh, okay.
There was in Miss Hartman's old room. There's pictures.
Wait,
Or Miss Mikowski's.
what was? There's the wall that's over there, and there's like all the things.
There's the wall that's over there.
Yeah, it's outside of Mr. Art's room. It's like the Bohr model. There's the other model. I can't think of the names.
Bro, I have like so many.
Yeah. Oh, he's doing it right.
How long did it take you to get rid of that?
We're done, but we have.
What was like going with like that star?
I don't know. It looks like you have a cookie. It looks like you know those tins of cookies. It looks like you have all. It's not fun. It's like the crown. No, yeah.
Oh, that is something this
Yeah, this is
y'all can fucking from this one.
something like that.
Those
Bomber.
Good. Okay.
I know.
Okay. So,
I know. He didn't say correct.
the idea of the atom has changed a lot over the years, ladies and gentlemen. And what we believe the atom looked like from its very earliest stages to what we believe it looks like now has changed quite dramatically. And there is evidence to suggest that even what we think we know today probably isn't 100% correct. There's probably more to the story too there. Phoebe went with the Jimmy Neutron atom. I do like that. You know, the one where you have the orbitals all around it in all different directions. But then she also went with more traditional, the Bohr model. Phoebe got it right, 2 in the first, 8 in the second.
Okay.
Good job.
Don't.
And then there's Josie, who also did a Bohr model, but she kind of
I did it
violates some
wrong.
rules. Luckily, we haven't talked about 1s2 and 2s2 and 2p6.
Yeah.
Things like that would have helped her out with this. I do like the fact that Josh included protons and neutrons in the nucleus. At least I think that's what those are supposed to be. And then he also included the electrons out there, although we kind of messed up on the total number of electrons in an energy level. But again, pretty good idea of what the atom looks like. Well, today, ladies and gentlemen, we are going to talk about the history of atomic theory. Now, that means we're going to go back and we're going to talk about where it started and who came up with what ideas and who did some very important things on it. Now, some good news and some bad news. The good news is I'm never going to quiz you on dates. The bad news is these are where I come up with a lot of the names on that yellow sheet. So it would be a good idea right now to take out that yellow sheet. And when we talk about Lavoisier and we talk about how he gave us the law of conservation of mass, you can write it down on that yellow sheet. So then when you get to the test, and the question is, the scientist who created the law of conservation of mass is a third period element with the same number as valence of electrons as there are d orbitals. You can have an idea of where it goes. Also, please take out those periodic tables that I gave you last week, ladies and gentlemen, because we do need to add something to those. We do need to add something to those, okay? So let's get that stuff out and let's get ready to get going here, ladies and gentlemen. And we'll go from there, okay? Take a look at it. Is there something you want me to change or anything? No. I would say copies of it electronically so people
Wait,
Joshua. Josh. Josh. No, that Josh, not this Josh.
Brass.
Achilles. Evie.
12, something.
Josh, now you Josh. Not that Josh, this Josh. Shenza.
Well, that's good.
Maddie.
And then my son's like kind of way right after.
Faith.
My son's like,
Jaden.
do they have those photos? Kind of in there.
All right.
So,
Morgan.
I did that, but I don't know.
Eric.
And then didn't I tried?
Hayden.
And then I wouldn't credit it.
Irvin.
I'm there.
JBG.
Why don't we have school?
Wait.
Because it's a day that was scheduled off for a random Friday off in February because the weather is so nice in Wisconsin that they feel you should go out.
It's because my birthday's a holiday.
Is it? When's your birthday?
Dream.
Oh, well, happy birthday, even though we won't be here to celebrate.
It's okay, because my birthday's a holiday.
Okay.
Where am I?
Last year we had the snow day.
What holiday is your birthday?
My birthday.
My birthday. Okay. National My Birthday Day. All right.
Cuba.
My birthday.
Okay. Oh, I guess there's another date. I'm at, oh, yeah, literally 110.
All right.
Hold on.
It's like right after my. Lily has a solo for a violin.
National Tile Day? When is that?
Her birthday.
On her birthday?
Back in time.
All right, Michaela Pierce, let's go. You can go do it next door right away. Get it out of the way. Come on. Bring your periodic table with you.
It's even harder.
Really?
Morgan Baptiste. No, it's not. It's not Morgan. No, it's not Morgan. Morgan Baptiste. Danny King. What's that? Oh.
Well, you can bring your periodic table with you because you're going to need it for sure.
Is this et al?
National Tennis Day. That's your own day.
Oh, that's why I can't find it because I wasn't expecting it to look like this.
National Banana Bread Day.
That's what happened with my phone. Like, it came with the K.
Alright,
K.
let's go.
K.
So, alright. Part of it was done on the computer, part of it was done on paper. I just put it all
Did you
in.
guys find it or think for
So, this first part is the one that's like,
Yeah.
Oh, that's so boring.
It is.
I'm kidding.
I'm not getting it complete.
I have to repeat a certain thing twice when the songs are turned up.
What was that? 15?
Yeah.
On the line.
Yeah.
15, yeah. I got it.
First one's from the bottom.
And they were all below the.
alright, ladies and gentlemen, wonderful, wonderful, wonderful. Okay. So let's take a look at the quiz from last week, ladies and gentlemen. Now, the part that is online I released to you. You can go back and you can look at it, ladies and gentlemen. But here are the questions to it. Okay. I printed them out and put an answer key to them. So again, you would have to be on your computer to be looking at your old quiz, which was released to you. Okay. Thank you for your drawings, by the way. You guys are all greater artists than I am. Absolutely no question there. The principal quantum number indicates what property of the electron. There's your answer for that, ladies and gentlemen. The azimuthal quantum number is what property? There you go. The subsidiary quantum number tells you that about the atom, or electrons basically. How many energy sublevels are in the second principal energy level? There you go. What is the maximum number of f orbitals in any single energy level? Here. When do the F's start? What level? Okay. Now, good point. There is a difference between when they fill the sixth level and when they exist the what level? One more. Fourth. So there is a difference between where they exist in the fourth energy level and where they fill, which is the sixth energy level down here. The same with the D's. The D's exist in the D's exist in the third energy level. They don't fill until the fourth. So that is the difference between them that we will put somewhere on a table in a little bit. All right. Okay. So the maximum number of d orbitals in any principal quantum energy level, half the number of electrons. The maximum number of electrons in the second principal energy level would be this, because of the s and the p's. What types of atomic orbitals are in the third? Now, again, these do not start filling till the fourth, but they do exist in the third. What color of light has the shortest wavelength? Again, that is of the ones that are given here. And in this case, this is the one that is the shortest of all of visible light as well. Okay? But if I don't give you this as an option, you have to figure out which one would be the next shortest of the ones that are given. What color has the most energy? That one again. Okay? How does the speed of visible light compare to the speed of gamma rays when both speeds are measured in a vacuum? All of them are at that speed. Questions? How are frequency and wavelength in light related? Inverse. Wavelength is going down, frequency is going up. Which of these has the highest frequencies? That one. The distance between two successive peaks on a wave is that one. And then the unit for frequency is that one there, ladies and gentlemen. Now, the electron configurations. Are there. If you use the noble gas core, it replaced this. And then they both would finish with this. So the part in parentheses here, or brackets, is what would have been in the noble gas core. I didn't do it here because it's the same as this one. And I didn't do it here and here because that's too much to write. That's why we use a noble gas core. But that's the way it should have been for your answers, ladies and gentlemen. Please take a look at it. And if you have any questions, please let me know. 15 points for the part that was done on the computer. The computer graded that for me. I just put the grade on there for you. 5 points for these 5 for a total of 20. Do you have any questions, ladies and gentlemen? Yes, no, maybe so. All right, ladies and gentlemen. So let's take out this. Okay? There's something that I thought about adding to it with my second period or with the class after you guys that I should have added with yours right away. So we're going to take care of that by doing that right away today, ladies and gentlemen. Okay? We're going to take care of that by doing that right away. And that is this, ladies and gentlemen. Underneath the group number 1, ladies and gentlemen, please put alkali earth metal. That is the name, the family name of that group of the periodic table. Alkali earth metal. Now that does not include what element though? Hydrogen, because hydrogen is not a metal. But that is the alkali earth metal family, ladies and gentlemen. Okay, and any element up and down from period 2 down to period 7 is considered an alkali earth metal. Question. Group 2 are called the alkaline, I-N-E, earth metals. Okay, they are the alkaline earth metals. Those were 2 of the earlier discovered groups of elements, ladies and gentlemen. That is why they were given those names. Group 13 has a more boring name. It is called the boron family. Group number 14 is called the carbon family. Group number 15 is called the nitrogen family. Group number 16, the oxygen family. Group number 17, halogens. Halogen means salt former. And group number 18 is the noble gases. By the way, noble gases are inert, unreactive, and they are monatomic. Anybody know what monatomic means? Okay, what's diatomic mean? 2 of the same atoms, right? Why are the noble gases monatomic? What does it mean? By itself means 1 atom, by itself, monatomic. They don't combine with other things. They don't combine with other things. Okay? Questions? Go into the carbon family and make a note. Carbon is the basis of life. Every living thing on this planet is carbon-based, ladies and gentlemen. That is the element that is the main ingredient in all living things. Questions? Okay. So those notes will help you as we go on and on, ladies and gentlemen. Any questions? Where I would be at right now, ladies and gentlemen, is I would take out your yellow sheet. Your yellow sheet that has all of the names on it, because as we go through this, ladies and gentlemen, you're maybe going to want to put some notes on there. Now, also, ladies and gentlemen, please do not yell at me. This history of the atom is not a complete and thorough history of the atom. These are just some people who did some major contributions to the history of the atomic theory. And unfortunately, ladies and gentlemen, 99%, well, all of them are men. Why? Well, because women weren't allowed to be scientists back then. And if a woman did come up with a great idea for science, she had to take it for scientific review before a committee full of men who would say your work was hogwash, it was shoddy. Then they would steal it and publish themselves and get the credit for it. Yes, guys, we've been doing this forever. Okay? Not giving women the credit that they deserve. So, sorry about that, ladies and gentlemen, but that is just the way it is. So, here we go, ladies and gentlemen. Let's talk about atomic history. Okay. First of all, the idea of the atom started with actually a Greek philosopher named Democritus. And it is about 400 BC. Now, again, I don't tell you that to expect you to remember that, but please understand that the idea of the atom started about 2,400 years ago. 2,400. A Greek philosopher named Democritus. Now, the story goes that he sat down to dinner one night and there was a loaf of bread in front of him and he cut it in half. And he got to thinking, could you cut things in half forever? Forever. Not literally, but figuratively. Or do you eventually get to some small piece of matter that you cannot break down anymore? You can't cut it in half. And he gave us the term atomos. Okay? He gave us the term atomos. And he said that atoms are indivisible and indestructible. Is he on your list? Yeah. Started the idea of the atom, said they're indivisible and indestructible. Those are the three things I would know about him. Gave us the term atomos. Okay? Thank you. Greek philosopher, not very important. This continuous theory of matter means that matter does have a smallest piece, have a smallest particle. Okay? Now, over the next, 2,200 years, not a lot of work was done on the atom. Because people weren't allowed to practice science. Why? Thank you. Religion became very popular. People found God, and God was the one who would take care of everything for you. Okay? So if you got sick, it was because you did something that you made God mad at you. So you weren't supposed to get healthy if you got sick unless God wanted you to. And scientists would try to make medicines, try to come up with figuring out things, and they were looked down upon by the church. They were looked as witches, and they would be burned. Okay? So a lot of scientists didn't work in public. They had to keep their work secret. Okay? So a lot of scientists used to do their experiments in secret. They would write them down, and only their assistant would be able to understand the work they did. And a lot of assistants got promoted to scientists after their boss killed themselves. Either trying the new medicine he made that would turn out to be poisonous, or possibly blowing himself up in the lab doing some experiments somewhere. So for a lot of the history, for a long time, ladies and gentlemen, there isn't any. It just, nobody wrote things down. Nobody shared things.
So there could have been like so many other things found out about like science, but they just died.
More than likely, they were found out anyway, but they would have been found out sooner, and probably fewer people would have died repeating the same experiment that somebody else did that killed themselves doing. Okay? So now we're going to go, ladies and gentlemen, to a man named Proust. Proust gave us something called the law of definite proportions. Okay? And he came along and basically said that compounds have a definite proportion to them. So, for example, water is a compound. And he found that the definite proportion in water was 2 grams of hydrogen to 16 grams of oxygen. Now, we know this is true today still. Because if you look at the periodic table, the molar mass of oxygen is 16. The molar mass of hydrogen is 1.01 times 2, which means the mass ratio for hydrogen to oxygen is 2 to 16 or 1 to 8. And Proust found this out about a lot of different compounds. He found out that there were these definite proportions in the compounds, meaning that all compounds were basically the same of the same substance. Okay? The same of the same substance. Okay? He had a theory that hydrogen was the building block for all elements. And that if you look at helium, helium's mass is 4 times larger than hydrogen because somehow hydrogen is the building block that makes up all of the other elements. Hydrogen is the basis. Now the sad part is, he's right. In the sun, in nuclear reactions, the sun takes tiny, tiny hydrogen atoms, slams them together, and makes helium atoms out of them. Takes a hydrogen and a helium atom, slams them together, and makes lithium out of it. So, while Proust didn't get credit for it, he was right. And it wasn't only until we discovered nuclear reactions and what's going on at the sun that kind of validated what he said. Okay? Now again, I'm not expecting you to write everything down. Proust on your list. Law of definite proportion. I put at least that down by him. Now again, you can use anything you write on there on your test. Okay? Lavoisier, ladies and gentlemen. Lavoisier was another scientist. Okay? And Lavoisier got to work with a new piece of equipment. A new scientific piece of equipment. He got to work with a balance, ladies and gentlemen. Not the balances like we have in the back, the digital ones. The balances that had 2 pans on each side. You put something on one side, you put something on the other side, and you could find when their masses were equal. Okay? And he did experiments with combustion, candles. Now, at the time, ladies and gentlemen, he ended up creating what is called the law of conservation of mass. Write that down for Lavoisier on your yellow sheet. You get a law, that's pretty impressive, ladies and gentlemen. Law of conservation of mass. He said that matter could neither be created nor destroyed. Now, at the time, ladies and gentlemen, people knew that if you put a candle inside a sealed container, it would eventually do what? It would burn out. Okay? They didn't know why. They didn't know why. But they believed that there was something in the air called phlogiston. That phlogiston was this magical substance in the air that caused candles to burn, and if you run out of phlogiston, the candle stops burning. But the only way you would run out is if you used it up, correct? Think about gasoline in your car. If you use up all the gasoline in your car, what happens? It stops. It stops. But the gasoline that was in the tank is what? Gone. So overall something is gone, correct? Used up. Well, what Lavoisier did is he did some experiments where he took burning candles, put them on the balance, sealed them up. And what he found was they did burn out, no question there. But their mass never changed. the total mass of the burning candle in the container never changed. Well, if you use up all the gas in your car, it's gone. There is no more. Your car would literally be what? Or lighter. Because with gas in it, that gas would add mass, right? Without the gas, it'd be lighter. Well, Lavoisier found that, you know what? The mass never changes. So it's not that this stuff got used up. He said the stuff had to be changed somehow. It's still there. The mass hasn't changed. But it's different. Again, we still didn't know about oxygen in the air and supporting combustion and all these things. They believed that there was this magical phlogiston. Okay? Little side note about Lavoisier. Some of you may have heard about him. Probably not knowing who he is, but you might have heard the story of him. Well, Lavoisier, what nationality was he? French. French were ruled by the king. And the one thing you don't do is piss off the king. Well, Lavoisier was getting to be a fairly decent scientist, and he thought he could piss off the king. So back then, when you pissed off the king, what did they do?
Chop your head off.
They chopped your head off. So he pissed off the king enough that the king said, you're going to go headless for a while, dude.
Oh,
Okay?
I know.
But at the time, there were a lot of people who thought that the guillotine was an inhumane way of killing people. And others said, what, are you kidding? As soon as that blade cuts through their head, they're dead. They don't feel the darn thing. Well, Lavoisier decided he would perform one last experiment, ladies and gentlemen. His last experiment was he told his assistant that when he got his head cut off, because they would reach into the basket and pick it up and show the crowd and go, this could happen to you. Don't piss off the king. He said, if I am alive after they cut my head off, I will give you a signal. Now, obviously, he couldn't talk because he had no body anymore.
Move his eyes.
He blinked his eyes. And the story goes that he blinked like 28 times or something before he finally closed them one last time and died. I don't know that I would be that dedicated to science that I would want that to be my last experiment, ladies and gentlemen. Actually, there is a story, though. Weirdest story ever I saw on Sunday morning of a chicken that lived for years after it got its head cut off.
Oh.
They cut it off, and they believed that when the farmer cut it off, he cut it off just high enough to leave enough of the brainstem there that the chicken would undergo respiration, would still breathe, and would still have the major functions of the body still going. And this chicken lived for years. And they used to have to feed it with a dropper down the cut off neck to give it nourishment. And they used to take it on 2 sideshows and show this chicken running around with its head cut off.
Mike.
So, excuse you?
Mike, the headless chicken.
Okay, there you go. Okay? All right. So, now we get to a guy named Dalton, ladies and gentlemen. Okay? Now, Dalton gets credit for being the father of modern chemistry. Dalton's on your list, ladies and gentlemen. He is credited with being the father of modern chemistry. Now we're talking around the 1800s, by the way. So we are talking about 2,200 years after Democritus said the atom was indivisible and indestructible. Dalton came along and he agreed with him. He said the atom is indivisible and indestructible. And he said every atom that is the same is exactly the same. And every atom that is different in some way from other atoms. I know it sounds like a no-brainer. But in reality, what he was doing and didn't know it was he was describing protons, neutrons, and electrons. He was right. Every different atom is different in some way. They didn't know what protons, neutrons, and electrons were, so he couldn't say that. He also said atoms could combine to make compounds. Well, Proust had said that before with the law of definite proportions, but Proust had a problem. His problem was sometimes carbon and oxygen combined, and the ratio for carbon and hydrogen, or carbon and oxygen, was 12 to 16. 12 to 16, okay? Or 1 to 4. But sometimes carbon and hydrogen would combine, and it was 12 to 32 mass ratio. Any idea why? 12 to 16?
Double.
12 to 32 is double that. We're talking carbon monoxide and carbon dioxide. Two compounds that use the exact same two ingredients, but in different ways. Well, Dalton came along and he kind of solved this. He came up with his atomic theory, and he came up with the law of what we call multiple proportions. The law of multiple proportions says that things can combine in more than one way. So hydrogen and oxygen normally combine to make water, which is a 2 to 16 or 1 to 8 ratio. But they also combine to make peroxide, H2O2, which is a 1 to 16 ratio. So they had different masses. Dalton explained this as saying different elements can combine in different ways, so they have multiple proportions. Okay? Multiple proportions. Questions? All right. Now came a man named Berzelius. By the way, again, we've jumped around quite a bit. We've gone from 400 BC to 1800s. But think about this, ladies and gentlemen. 1800s, that was 200 years ago. That was around the time Mr. Arts was born. Okay? Okay? So, again, you know, a little bit more relevant. Berzelius came up with the relative atomic masses of many of the metals on the periodic table. He came up with the relative atomic masses of many of the metals on the periodic table. I believe he's on your list. Probably a good thing to write by, considering there aren't a whole lot of things. And he did it by comparing metal oxide. By the way, your list is in alphabetical order. So I would look near the top where the B's are. Oh, Mr. Brand, that's helpful. Why didn't you tell me that 3 days ago? Right? So he found the relative atomic masses of many of the metals on the periodic table. So now you're sitting here, ladies and gentlemen, you're going, what the heck? Why do I care about this guy? Well, because the guy who found the relative masses of many of the elements on the periodic table is in the third period and has 4 valency electrons. Third period, 4 valency electrons, somebody. Third period, 4 valency electrons, somebody. Third period, 4 valency electrons, somebody. What? No, it is not beryllium. Beryllium is in the second period and has 2 valency electrons. Other than that, you were right there, Josie. Third period, 4 valency electrons, ladies and gentlemen. Silicon. Silicon. If you're going to miss the easy ones, you're going to struggle like hell on this next test.
Yeah.
Okay? Struggle like heck. Especially since on that last periodic table we were working with, at the very top, we have valency electrons up there. Oh my gosh, let's not look at our resources, whatever we do.
Well, it was out in front.
I know, it was in front of me. That was the problem, Mr. Brand. It was right there in front of me. I couldn't look at it. Gosh. All right, now we get to a man named Davy, ladies and gentlemen. Okay? Now, yes. Davy is the man who is credited with discovering many of the alkali metals. Sodium, potassium, lithium, rubidium, cesium. I don't know if he discovered France, but he discovered most of the alkali metals. Maybe he discovered them all. Okay? So the element named after the scientist who found most of the alkali metals is in the period that represents a d orbital. What period represents a d orbital? What number represents a d orbital? 2. Second period. Second period. And is a -1 ion. Second period, -1 ion. Second period, -1 ion. Is this thing on? Second period, -1 ion. Fluorine. Very good. That's where Davy might go. Or at least the symbol for the element named after him. Okay? What?
No, continue.
He found more new elements than any other person. Davy is credited with finding more new elements than any other person. Now, actually, ladies and gentlemen, he didn't find the alkali metals alone, though. He found them in what? He found them in college, yes. He went to Penn State, and there in Penn State, they had a bunch of elements there, and he's like, oh, look, these are the alkali. No! Now, the noble gases, those were found alone. Why?
Oh, because they don't combine.
Okay, why aren't the alkali metals found alone?
Because they combine.
So how are they found?
Together.
In compounds in nature. And he was able to isolate them and find their masses. Okay? So again, many of the elements on the periodic table you will not find alone. Gold, yes. Silver, yes. Carbon, ain't happening.
How do
You're
you
not.
find it in nature?
What?
How do you find it in nature?
Well, he would discover a different mineral, and they'd break it down and figure out what was in there, and boom. Okay, this has got this alkali metal in it.
So were these scientists like also like archaeologists where they're digging up bones and stuff? Like,
No, I don't know these guys personally.
like how do they get the?
How do I know if they're Randy Travis
Well,
fans?
how
They're
they-
digging
how
up bones. I'm digging up bones. No, I don't know.
Well, yeah. Did they like? How did they find? They can't just like.
First of all, bones aren't made. Bones don't help you because
Like
these are
rocks.
minerals.
Well, okay, but you're not just like walking down the street and you find a funny rock and you're like, oh, that's.
Who
not
knows?
that,
Maybe that's
that.
exactly what they did because the streets weren't paved back
And
then.
then I should be able to find these then, like anywhere.
The problem is somebody already found them. Okay, so let's get to Dobereiner, ladies and gentlemen. Dobereiner is an interesting person. Dobereiner is credited with trying to set up a periodic table. And he created something called triads. Three. He put elements in groups of 3 because they had similar properties. So he created these triads. He put magnesium, calcium, and strontium together. Wait a minute, what? Magnesium, calcium, and strontium together? They're right above and below one another on the periodic table, aren't they? He put iron, cobalt, and nickel right next to each other on the periodic table. Copper, silver, gold. Did a pretty good job putting elements together based on their properties, but he only did them in groups of 3. He created these triads. And he was the one who was basically made the first real attempt at organizing the periodic table. Okay? First one to make an attempt at organizing the periodic table. Then Newlands came along.
Oh my god.
You know Newlands?
I just see some happy things.
Oh, okay. Well, Newlands, he's different than Oldlands. Okay? Younger version. Okay? Newlands was a musician who turned to science. But it was the fact that he was a musician that helped him, ladies and gentlemen, because he created what is called the law of octaves. Again, law, impressive. Octaves, what is octa? 8. Created the law of octaves. He said there is a pattern in the elements that we have that repeats every 8. Every how many?
8.
Every how many?
8.
How many groups are on that periodic table that we just put the names on? 8. The 8 main groups, these 2 and these 6 over here. He was on to something, ladies and gentlemen. Created the law of octaves, which basically says that there's a pattern that repeats every 8 elements, which is why lithium and sodium are underneath each other with potassium beneath them. And as you move across this group, okay, different things change, but when you come back to the start, this has got similar patterns to the ones that were above it. Okay? Meyer, ladies and gentlemen, he was a German man. And he set up a periodic table. Actually created one. We didn't like it. Okay? His periodic table didn't get accepted. Whose did?
How do you say it? Mendeleev?
Mendeleev.
Mendeleev.
Mendeleev. Mendeleev was a Russian scientist. This guy was always in a hurry, ladies and gentlemen.
Oh.
Always in a hurry.
To leave.
Could be. Maybe that's why they said, hey, look, Mendeleev. Or people wanted to get rid of him. Hey, Mendeleev, get out. Okay? Anyway, he also set up a periodic table. And it's his that we accepted, not Meyer's. Okay? It's his, we accepted. And there was a good reason we accepted his. And that was because he not only set up and organized all of the known elements, ladies and gentlemen, he left gaps or holes in his periodic table. Now you may be saying, gaps and holes, that seems dumb. He set up for elements that had yet to be discovered. Now, I want you to imagine this. You remember that scientific committee that I said would steal all the women's work that they did, claim it for themselves? Well, Mendeleev and Meyer go to them to present their periodic tables. And Meyer's like, here, I've organized all the known elements on the periodic table. Here's the way we should present them to people. And Mendeleev came along and said, hey, dude, your system sucks. Mine is much better. And people are like, well, why is yours better? Well, you see that blank spot right there? That's an element that is yet to be discovered. And I know that it's out there, but we haven't found it yet. What do you think people thought?
It was
He
cool,
was a
cool.
witch because
They thought, dude, you are nuts. You can't make your periodic table the way it's supposed to be. So now you're telling me there's elements out there that we're going to find later on that will fit into your periodic table? Yeah, right. And it wasn't until they started finding them. And after they found them, he said, hey, you know what? This element, it's going to have this mass. This element, it's going to have this property. This element, it's going to do these things. And they started to find them. And he was right. That they said, dang, nice job, dude. Okay?
I don't know if you'd show it.
And we set up the periodic table. Now, we are lucky here, ladies and gentlemen, because, again, Mr. Arts was born in the 1800s. When he was in school, they had this periodic table in his classroom. This periodic table is from 1930, ladies and gentlemen. Okay? 1930. So imagine 100 years ago, a student sitting in the class. This would have been the periodic table on the wall. 85, ladies and gentlemen, didn't have a symbol. Didn't have a name. 87 didn't have a symbol and a name yet. There wasn't anything over 92. Nope. Not yet. Okay?
no, for real.
So again, ladies and gentlemen, this is kind of a cool piece of history that was just laying around East High School. We took and put it into a frame, put a nice plastic cover in it to stop some guy from spilling coffee on it, or someone from trying to fill in things that they shouldn't have. So unfortunately, ladies and gentlemen, if they hadn't probably done those things, this would be my retirement account right here. Selling it, but unfortunately they ruined it. Go ahead.
What did they like invent the language?
Oh, God, we're not even close to that yet. Because to be honest, where we're talking, we still don't know anything about protons, neutrons, and electrons. Early 1900s. Still don't know about protons, neutrons, and electrons. So when Mr. Arts was a kid growing up, they didn't have protons, neutrons, and electrons. This used to be a lot more fun when he was in the room next door, ladies and gentlemen. It really did. It's not the same now that he's gone and he can't poke his head in and go something about him and dirt, and I don't remember which one he said came first. But anyway, ladies and gentlemen. All right, let's get to Melville. Melville, this is not the author. Anyone? Anyone? Melville's famous book? Really? Whale and a guy? Very good, very good. Not the same Melville, ladies and gentlemen. He used what is called the Crookes tube, ladies and gentlemen. He used the Crookes tube. That's not a tube that you stole from somebody. I know what you're thinking, 90 degrees. Okay? I know what you're thinking. Okay? Damn, someone stole my Crookes tube. There's a crook in the building.
Whoa.
Exactly.
That's gonna raise the.
It's Mr. Johnston.
It probably is. I'll bet you it's Bulkowski. Hang on 1 second.
Call her.
Ángel, Angel, cierra la puerta, papi.
¿Sí la puede abrir?
Sí, tiene su llave.
Todos más que güey.
Cierra la mensu.
All right, I got one more shot here, ladies and gentlemen. Hang on. Hang on.
Cierra la papi. Crook.
I'm not gonna get do that. I'm gonna do more.
There's a crook.
Not a good escape from project.
I wish we could just save this pin for your product.
These are great references. Beating my dad.
None of that.
It's
Being
cool.
genuine.
I think it's or whoever's looking for his crook.
No crooks.
I find out who stole my crooks too, ladies and gentlemen.
I'll find it.
Yeah, but it isn't the tube I wanted to show you, it's what the tube does that I wanted to show you.
We're body shaming.
Yes, we're body shaming a tube. Is it in the back?
Oh, well,
Not back there. Why would I have put it back there?
Call Miss Whitehouse and tell her, hey, give me my tube back.
One last check.
It was not even two, man. It's
Really just walking in this one.
What is she using it?
Pasó.
Okay, but it wasn't forward.
What if it's back there?
Never been in it.
All right, I'll yell at people at lunch and find it
What
for
if
you.
it's back there? Like,
It's not!
well, I'm looking at what if I see it?
Okay, point it out to me.
Go back there.
Point
You don't even know what it looks
I
like.
just Googled it.
Okay. So anyway, Melville used a Crookes tube and found that gases create different colors. He found that if you take an electric current and you put it through a gas, it creates different colors, which is very important for Wisconsin now, ladies and gentlemen. Why? Because every bar in the state has neon lights in it, ladies and gentlemen, and that's what it's from. Putting an electric charge through neon gas will cause it to light up and turn colors. Yes and no. Charged particles in the atmosphere cause the atmosphere to glow different colors. Yes. Yes. Okay. But remember, we would have a hard time finding the noble gases. Why? Because they're gases. They don't combine with anything. They stay to themselves. So this was a way we could detect them. Putting an electric charge to them and seeing what color they glowed, because different gases glowed different colors. Okay? Millikan, ladies and gentlemen, Millikan did a real cool experiment. He did what was called the oil drop experiment. He was able to take a fine mist of oil and suspend it between two charged plates. And he could get the oil drops to move one way or another depending on how he adjusted the charge on the plates. Now, he didn't do it, but he was leading us to finding the charged particles in an atom, which are
Close to.
no, the charged particles within an atom.
Oh, protons, neutrons. Protons,
And
neutrons, electrons.
oh, they're not charged. Protons and electrons are. What?
Are they the same people?
Who?
I don't know.
What do you mean?
Right there.
Millikan and Melville? Oh, wait, you're saying Milliken might be this guy who's on the board, right? Oh, I see what you're saying. There's a spelling error. It's E-A-N on there and it's E-N on here. Yes, same guy. Sorry.
Milliken.
Yes.
Milliken.
He actually was able to find the charge on an electron. Yes, sir. Go ahead.
Wasn't there another guy that uses the Crook tube later on?
A Crookes tube later on? Yes. Thompson. Yes. So, but he was able to figure out what the charge on an electron. He didn't know what an electron was yet, but he was able to find the charge on it by being able to charge these plates and suspend oil drops between them and get them to move back and forth. Okay? Thomson, here we go. Thomson gave us the plum pudding model. Now, you all in physical science, if you had physical science, talked about Thomson. By the way, the ones that are on the list that you've talked about were Democritus, were Dalton, and now we're Thomson. Thomson gave us the plum pudding model of the atom. He found the electrons. Put that down for Thomson. He found the electrons. That is what he did. He found negatively charged parts to the atom. Now, how many of you have ever had plum pudding? Yeah, me neither. Never in my life. But you know what I did have when I was a kid? I had chocolate pudding, which has nothing to do with plum pudding. But my mother, when she would make chocolate pudding, before she would serve it to us, would take cherries and hide them in the chocolate pudding. Now, chocolate pudding, good. Cherries, good. Put the two together, you got greatness, ladies and gentlemen. You really do. Okay? It's kind of like me. Good. My wife, good. Put us together. Never mind. Anyway, ladies and gentlemen.
Oh my.
So, you'd be eating your chocolate pudding, and every once in a while you'd get a cherry. Nice treat. But that's kind of what Thomson said that the atom looked like. There were these negatively charged particles scattered randomly throughout it. So he said it was like a plum pudding. Nowadays, they will say he said it was like a chocolate chip cookie or chocolate chip ice cream, where the chips are randomly spread out throughout the cookie. He said the electrons were randomly spread out throughout the atom. Now, this took what Dalton and what Democritus said and trashed it.
The ratio thing?
No, the fact that the atom is indivisible. There is now smaller piece than the atom. These negatively charged particles in it. And if you have a negatively charged particle, you probably have a what? Positive. He didn't find it, but he theorized that there was a positive charge to it. Was that your only question?
Yes.
Okay, good. All right. So basically, he found that the atom was divisible. Okay, questions? Yes. Do we have the microscope by now? I would believe so, but even if we do, you can't see an atom with it. Still way too small. The microscopes that can see it now are electron microscopes, and they are bigger than this classroom to be able to see the actual atoms of things. Yes. An electron microscope would be about as big as this classroom. Okay? All right. So next, ladies and gentlemen, came a man named Rutherford. Now we're getting into the scientists who you probably heard about during physical science. Rutherford did what was called the gold foil experiment. He took gold foil and pounded it into as thin a sheet as he can get. And gold is unique because gold can be pounded very thinly. Very thinly. Matter of fact, only a few atoms thick is how thick you can get gold. And then he took and he fired what are called positively alpha particles in it. He fired them at the gold. Now, a positive particle and a negative particle should do what? Attract. Yes. Well, when he shot these alpha particles at the gold foil, he found some weird things. Number one, most of them went right straight through. Meaning? No. Meaning there's a lot of empty space. Now think about this. Think about a soccer net, ladies and gentlemen. Okay? The one good time we'll use soccer as an example. I'm not calling it a sport, but we're using it as an example. If you kick a soccer ball into a soccer net, what happens? What? It gets caught. What would happen if you shot a golf ball into a soccer net?
It probably goes through.
Most of the time it would go through. Why?
So small.
Because the holes are big, right? And the ball is small. Well, that's what Rutherford found in the atom. Could the golf ball hit something, though? It could hit the net. It might hit the strings or where they're tied or whatever. Well, Rutherford found that sometimes he hit something. But instead of being attracted to it, it bounced away from it. So he found the nucleus. He found the positively charged center of the atom. Didn't find the proton yet, but found the positively charged center of the atom. Okay? And he gave us the solar system model to explain it. He said that the electrons orbit the nucleus like the planets orbiting the sun. Kind of sounds a little crazy now, right? But 1930 periodic table on the wall, ladies and gentlemen. Planets' valence. Planetary electrons in completed orbits. They taught this. They believed he was right. They believed that the electrons moved around the nucleus like the planets move around the sun. Doesn't have it on here. I thought it did. I thought it had Josie's Jimmy Neutron atom model.
I know, that's Phoebe.
Or Phoebe, sorry.
Mine was stupid.
Sorry. No, they were fairly accurate, the models that had existed in the
Mine was
past.
wrong.
All right, now came along named Niels Bohr, ladies and gentlemen. Niels Bohr proposed quantized electrons. You can partially blame him for quantum mechanics, ladies and gentlemen. You know, those four numbers that describe the electron, you know, the principal, the subsidiary, the azimuthal, and the magnetic spin. Okay? He said the electrons were in energy levels, not in orbits. And that electrons could jump from one energy level to another. But if they jumped, you had to put energy in. And then to go back down, they had to do what? Release energy. How did they release it? They released it as light. Different colors of light. So on the wall back there, ladies and gentlemen, there is a poster that says spectrum. Every element on the periodic table has a unique fingerprint. Every element on the periodic table will give off light in very unique, different wavelengths. Some red, some orange, some green, some blues, some yellow, whatever. It's a fingerprint that'll tell you which element you are looking at, ladies and gentlemen. Okay? Now, Planck gave us what?
Energy and frequency.
Gave us the constant that related energy frequency. Blame him for the quantum mechanics stuff, ladies and gentlemen. Okay? Blame him for the quantum mechanics stuff we were doing at the start of this unit. Gave us quantum numbers. And he gave us the constant that relates energy and frequency. Yes, sir?
Is that why when you have salt fall into a fire or something, the color changes?
Yes, sir. That's also the reason for fireworks. The metals in fireworks, so you might have done a flame test in physical science where you took the sticks and put them into the Bunsen burner and they glowed a different color. That's all about those electrons moving between energy levels. Okay? And it may be moving from an S to a P, an S to a D, might be moving from the third to the fourth energy level, third to the fifth. They only moved in certain ways. All right, Moseley, ladies and gentlemen. Moseley is the guy who found the proton. So the element named after the man who found the proton is a man-made noble gas. Someone? Man-made noble gas. Someone? What? Man-made noble gas. Those are the man-made ones, right? Anything on that bottom row.
Magnesium.
So all of these, ladies and gentlemen, all of these here, those are man-made. Those are man-made. And he helped us set up our current periodic table by atomic number. Didn't change Mendeleev's periodic table, but it allowed us to now say, okay, it's in order by hydrogen 1, helium 2, lithium 3, beryllium 4, so on and so forth. Questions? All right, Heisenberg. Heisenberg gave us an uncertainty principle. Heisenberg said it is mathematically impossible to tell the speed and the location of an electron in an atom. You want to know the speed? I can tell you how fast it's moving. I can't tell you where it's at. You want to know its location? I can tell you its location, but I can't tell you how fast it's moving. That is the uncertainty principle. You can either predict the place or how fast an electron is moving, but you can't predict both. Can't predict both. Questions? Okay, I got a few minutes. I got a few more to get through. All right. Pauli gave us the exclusion principle, ladies and gentlemen. Pauli gave us the exclusion principle. He said no two electrons can have the same set of 4 quantum numbers. You can't do it. 2 electrons cannot have the same 4 quantum numbers. That is why there are only 2 electrons in the S. Because one is spinning one way, one is spinning the other. If you try to put a third in there, it would have the same quantum numbers as one of the other electrons in there. That is why in the P's there is a maximum of 6 electrons, 2 in every one of the 3 orientations. Otherwise, you would have to repeat your quantum numbers. That is the exclusion principles. No 2 have the same. Avogadro, what did he do?
Well,
Gave us the mole. Okay. Said that 1 mole of any gas, 22.4 liters. Okay. Avogadro's number. Come on, keep it straight. Formula mass relative to carbon. In other words, ladies and gentlemen, can we really measure the mass of a hydrogen atom? No, mass is way too small. Atoms, we don't have a balance in the world that we can measure. But we do know that hydrogen is about 1/12 or 1/12 the mass of carbon. Everything on there is relative to carbon. Okay? Newton gave us figs. No. He said white light was made up of the colors of the rainbow, and actually Newton's the guy who got science going.
Are they the same
Because-
Newton or 2 different Newtons?
Isaac, that's the guy we're talking about. What? Isaac Newton did not give us figs, dude. Stay with the program. I didn't have to explain that to you. He said white light is made up of all of the colors of the rainbow, and he is the one who got scientists to start writing and sharing information. He's the one who did that. Newton had a phrase, and his phrase was this. He said, if I have seen further than other men, it is because I have stood on the shoulders of giants who came before me. He recognized that there were a lot of scientists who did a lot of work that made his life easier. Now, he was able to take their work and go further with it, but he's the reason for Roy G. Biv, ladies and gentlemen. He's the one who figured it out. Questions? There you go. There's the history of the atom in one day, ladies and gentlemen. Awesome.
That was cool.
Awesome, awesome, awesome.
That was cool.